Let me walk you through how mixture of experts architecture works on a distributed cluster. From what we know in the open source inference code and the technical reports, they shared that DeepSeek V3 cluster consists of 2 nodes. Each one has 8 H800 GPUs connected with NVLink and InfiniBands across nodes. Each GPU is assigned a rank and also has exactly the same copy of gate weights. There are 256 experts in the DeepSeek V3 split equally across each GPU. From the previous layer, each GPU also holds exactly the same copy of X-tensor input, so the gates on the forward pass calculates and chooses which expert tokens will be routed to, and then sums all the expert results into local Y experts I. And the GPUs that didn't have any routed experts, they just hold tensor of zeros. The next step is to synchronize all Y experts to sum them up, so each GPU has the final Y experts tensor. If you're not familiar with how it's done through the ring all reduce operation, please continue watching, otherwise skip to the next section. The all reduce operation defaults to summation. Its primary purpose is to collect partial results calculated by individual GPUs and combine them into one final answer. Let me show you exactly what I mean by this. Imagine we have a simple 1D tensor consisting of 4 elements, and we want to distribute it across 4 GPUs. In this case, we split the tensor into 4 equal parts or chunks. We assign each GPU ownership over a separate chunk. For example, GPU 1 owns chunk under index 0, GPU 4 owns chunk under index 3, and the same applies for the rest of GPUs. Each GPU does its work and calculates the result for the specific part it owns. Let's say GPU 1 calculated that the index under the 0 contains value 1, GPU did a calculation for index 1, which is 2, and the final sum that we want to obtain is 1 plus 2 plus 3 plus 4, so the final state of the tensor will be 10, 10, 10, 10. How do we actually achieve this? Through a highly optimized operation called ring all reduce that comprises 2 phases, and one is reduce scatter. So let's talk about the first phase. All GPUs are connected in a ring. They form a closed circle where GPU 1 talks to its right neighbor GPU 2, GPU 3 talks to GPU 2 talks to GPU 3, GPU 3 talks to GPU 4. And we run this for n-1 turns, where n is the number of GPUs. Here's what happens on the very first turn. Each GPU takes the chunk it efficiently owns. For example, GPU 4 owns chunk under index 3 and passes it to its neighbor GPU 1. And what is specific to this first phase is the addition. So GPU 1 takes this value 4 and adds it to the value under exactly the same index as it came from. So let's see the results. This is the first turn where each GPU does calculations simultaneously. On the second turn and all consecutive turns, the rule is simple. Each GPU sends whatever chunk was updated the last. So if GPU updated chunk under index 3, then on the next turn, it's going to pass value 5 to its neighbor GPU 2, who's going to add it to the same index under 3. And the last turn. So at the last turn, you can see that on each GPU, there is a true value. For GPU 1, it's under index 1. For GPU 2, it's under index 2, etc. This brings us to the second phase called all gather, where each GPU sends the last updated value to its neighbor. But what's different this time, that when GPU 1, for example, receives the value from GPU 4, it doesn't add it, but overwrites it. So GPU 4, last updated value for it was under index 0, which is a true sum, 10. Then on the next turn, it's gonna send the value 10 to GPU 1, and then GPU 1 is gonna override whatever's under index 0 by this value 10. And we're gonna run it for exactly n-1 turns, as previously. Turn number 1, turn number 2, turn number 3. So you can see that at these points, all the values on each GPU have reached the final summation. Another part of the equation is shared expert that consists of matrices again of W1, W3, and W2. And in order to understand how it's distributed across a cluster, let's look at the DeepSeek's inference code that shows that it's implemented with a column parallel and row parallel approach. To understand it better, let's look at this concrete example with an input tensor X and a weights matrix W, and we want to distribute matrix multiplication across two GPUs. So as you can probably already infer from the name, column parallelism will split the weight matrix W vertically into two chunks, and the first three columns go to GPU 0 and the last three go to GPU 1. Remember how matrix multiplication works. We calculate the dot products between each row of the X and a column of W. And because of this rule, every GPU requires an exact full copy of X. So then each GPU performs its own matrix multiplication using full X and its chunk of columns. And finally, to synchronize and build a complete output tensor, we simply concatenate results from both GPUs column-wise. Now let's look at the row parallelism. This time we split the weight matrix W horizontally, row-wise. The first two rows are sent to GPU 0 and the remaining are to GPU 1. Because we sliced the weights horizontally, the math requires us to slice the input matrix X vertically, column-wise. We copy the specific chunks of X to each GPU, and then each GPU does its matrix multiplication, calculating the dot product between X and W chunks. And mathematically, in order to come to the final answer, what we need to do is to sum these partial results using all reduce operation. Let's see on the simple example how the shared expert's output will be calculated. So we start by splitting W1 column-wise, and each GPU multiplies the full input matrix X by its own chunk and applies the non-linear activation function. At the exact same time, we also start doing it for W3. And after the matrix multiplication is over, each GPU holds two partial results in its local memory. And because these two tensors are of the same size, we just do the element-wise multiplication. And finally, we need to project this data back to its original shape using the last matrix W2 that we parallelize row-wise. So each GPU then calculates its own partial result for the output tensor Y that is then synchronized with ring all reduce operation. So let's go back to this distributed view. Again, we distribute each matrix column and row wise across all the GPUs available on the cluster. And then using the exact same copy of X, each GPU calculates partial results for Y shared, and then using ring all reduce, this Y shared is synchronized so that each GPU then holds final Y shared tensor. And that concludes our deep dive into the mixture of expert architecture inside DeepSeek V3. I really hope this breakdown helped you form a strong intuition so that you can understand how this mixture of experts works under the hood.